Hello, my name is Dmitrii Kosarev and we are working on relational synthesis for pattern matching. Functional programs use pattern matching a lot, and efficient compilation of pattern matching is required for efficient compilation of functional programs. There are two main approaches for typed functional languages. Decision diagrams guarantee you minimal amount of checks performed. Compilation to backtracking automaton guarantees you lesser code size. We propose a third approach based on program synthesis. This is an example of pattern matching where it can be non-trivial. On the left you can see matching of three boolean values. Semi-optimal compilation scheme is in the middle. It consists of 6 if expressions. The most effective compilation scheme is on the right and it has only 4 if expressions. Here you can see main contributions of our work. We encoded pattern matching synthesis problem in miniKanren using two relational interpreters, and we got a formula with a universal quantifier. We performed a few transformations to replace this universal quantifier by a finite set of examples. Also, we applied an optimization for synthesis, and this optimization reminds branch and bound method. And to implement it, we added a new primitive called structural constraint. This is a syntax of two languages we used. Many things are omitted for simplicity, but we can reintegrate them in the similar manner as other papers do. On the left you can see a syntax of pattern matching language. All scrutiny's types are algebraic data types. We only support wildcard patterns and constructor patterns. The declarative interpreter of pattern matching takes a scrutiny and a number of patterns, and it returns an I, an index of the branch where execution should continue. If this index is k plus 1, it means that no patterns suit this scrutiny, and pattern matching is not exhaustive. On the right you can see a language of compiled representation. We can access subtrees of scrutiny using a bullet for scrutiny itself, and we can write a natural number on the right side of matchable construction. It will allow us to access to the nth subtree of this part of scrutiny. We have two kinds of expressions in this language. The return expression returns the branch index, and switch expression checks that part of scrutiny starts from specified constructor, and if no constructors suit this scrutiny, execution continues in otherwise branch. So we implemented two relational interpreters in miniKanren and prepared a synthesis algorithm using them. The formula says that for every possible scrutiny and for every possible branch index, our two relational interpreters should behave the same. In this formula, a circled question mark represents a synthesized program. The positive thing of this encoding is that it is easy to write two relational interpreters, and it will be easy to slightly change them when our languages will slightly change. The downside of this encoding is that we have a universal quantifier in formula, but miniKanren isn't really good at dealing with universal quantifiers. We also have disequality constraints under the hood, so using eigen is not an option too. So we decided to eliminate this universal quantifier. For every concrete pattern matching, we know the type of scrutiny, the patterns used in this pattern matching, and we can compute maximal depth of these patterns. The idea is to enumerate all inhabitants of scrutiny's type until certain depth. Use them as examples and replace universal quantifier by a finite conjunction. There is a possible performance problem because the number of examples can be, in worst case, exponential. This is an example of pattern matching where we match a list of some values. There are two patterns with maximal depth 3. The set of all inhabitants bound by the depth 3 is a 3-element set. And this set is a complete set of examples required for this concrete pattern matching. But in some cases, enumerating examples bound by the depth of patterns is not enough. Like in next example, where we match a list with two patterns, empty list and wildcard. The depth of these patterns is 1 and all inhabitants of the scrutinous type bound by the depth 1 is a singleton set which contains only empty list. If we run our synthesizer on this set of examples, it may give us a program in the bottom, which for empty list returns 1 and otherwise it also returns 1, which is obviously a wrong compilation scheme, but on this concrete set of examples it behaves the same as original pattern matching. This means that our set of examples is not a complete set of examples. Enumerating inhabitants until the certain depth of patterns is not correct, but we can repair this algorithm. What we actually do is that we evaluate the depth of the patterns and synthesize all inhabitants of scrutinous type, but on the depth h+1 we use a single predefined per type inhabitant. If the synthesized program doesn't look too deep into scrutiny, this algorithm will give us a complete set of examples. But this set of examples still will be exponential in worst case, although there are some simple observations that can reduce this set. In this example, we match 3 boolean values with 2 patterns. The pattern matching doesn't really care about contents of the first and second component of the triple. So we can reduce our set of examples using only 2 examples if we forbid our synthesized programs to look into first and second component of the triple. It will allow us to reduce example set from 8-element set to 2-element set. Our third contribution is an optimization that reminds branch and bound method. The idea is if our current estimate of answer is longer than already found minimal answer, then we can prune this search branch. To implement it, we modified miniKanren's run primitive and added a new primitive called structural constraint to perform actual pruning. Structural constraint takes a logic value and performs reification in a current state. Also, it takes a predicate which decides what to do with reified value. In our case, if the size of reified synthesized program is too big, we can stop the search in the current branch. But in other case, it continues search without doing anything interesting. There are a few subtleties with structural constraint. It may take or may not take into account disability constraints. It can be used to implement other constraints, for example, absento from the seminal paper about synthesizing quines. It also deals with reified values, so it can perform solve. We need to say a few words how we compute the size of synthesized program. We decided that the size of return expression is 0 and the size of switch expression is the number of its branches. The size of whole program will be the sum of sizes of all switches in it. Our minimization criterion will be to reduce the size of synthesized program, but in literature you can find others in the minimization criteria. For example, the depth, the branching factor, and others. This is an example from the beginning of the talk. We are matching three boolean values and our synthesizer in 1.5 seconds gives us an answer of size 6. And after half a second more it gives us an answer of size 5. And after half a second more it gives us answer of size 4, which is an optimal answer for this concrete pattern matching. Our approach currently doesn't scale well for big programs. This is an example from PCF interpreter from Gordon Plotkin's paper. It has many clauses in it, it has many constructors in scrutinous type, and to apply our synthesizing we will require to generate 11,000 of examples, which is a lot. But if we reduce this PCF program by types and by clauses, for example, if we left only 2 clauses, we will require 5 examples. If we left 3 clauses, we will require 20 examples, and in 1.5 seconds it gives us first answer of size 7, and after a second more it gives us an optimal answer of size 5. And after that it spends tremendous amount of time proving that there is no better answer for this program. So our conclusions. We encoded, our contributions is that we encoded synthesis of pattern matching using 2 relational interpreters. We performed some work to eliminate universal quantifier that appeared on the road and replace it by a finite set of examples. We also implemented branching bound optimization of synthesis, and to do that we added a new primitive called structural constraint to our implementation of miniKanren, which is called a Kanren, and it is a typed embedded of miniKanren into strongly typed functional language OCaml. There are areas of possible improvements. The main problem with our synthesizer is performance. To somehow fix it, we can try to improve reification of structural constraints, to improve reification needed for structural constraints, to make structural constraints run faster. We also can use finite domain constraints instead of disequality constraints to better control the order of branches in switch expressions. At the moment minimization is not used because we are using disequality constraints, and we are looking for more optimal ways to generate non-exponential set of examples. If you have any ideas how to generate non-exponential sets of examples, these ideas will be really appreciated. This is all. I hope that you enjoyed the talk. See you next time.